Hi, everybody. In the last video, we learned how neural networks really mimic the human brain and how they really make the decisions. Here in this video, we're going to dive even deeper. We are going to make the whole thing deep neural networks in comparison to just neural networks. What's the difference? Neural networks got layers, input and output, but in deep neural networks, we got hidden layers, which make the whole algorithm pretty deep. And that's simple enough to understand. It's deep neural network. What are the advantages? It learns better. How does it learn better? What do we do with it? One of the biggest testimony of deep neural network is generative AI algorithms. They all are using this idea of deep neural networks. Whole industry of AI is dependent on the idea of deep neural networks. We are making plenty of these layers stacked together and trying to learn the data, just like a human brain would do. We got all those kind of neurons that we have in our head, and the same idea we are implemented in the deep neural networks. Nothing too fancy. It's easy enough for a layman to understand. And that's how they came up with this idea of deep neural networks. All right. What are we going to learn in this? The problems that are associated with deep neural networks to be an expert in deep neural networks. We're going to learn about vanishing and exploding gradients. How do we detect an object using deep neural networks, like image processing stuff? We're going to alter the learning process. A child has a certain learning process. He's learning every day from the day he's born. Initially, they say that the newborn have the highest learning capacity. As you grow older, your capacity to learn kind of reduces, tapers down. And the concept is similar. We're going to play with the learning rate, and we have some functions to play with the learning rate. All right. We will learn about supervised learning for the face detection. Face detection. A lot of algorithms are detecting faces. China is one of the biggest example. US, like when you enter, like on the port of entry, they detect your face and kind of know who you are, even though you have not yet scanned your passport. So all this is using deep neural network. All right. So we're going to learn on how to choose the right activation function and what's the math that goes behind, what's the science that goes behind choosing the right activation function. We will learn about optimizers, learning rates, and the rate at which the model learns the best. We're going to learn about techniques to reduce overfitting. This idea of overfitting we have on and on and on talked about in previous videos. We got to prevent overfitting, otherwise our model is no good. So the popular techniques include dropout, regularization, and early stopping. Dropout simply indicates we are dropping out something, and in this case, that's the neuron. Regularization we already talked about in previous videos, like L1 and L2 regularization, and we can also do early stopping. And we have talked about early stopping in our previous videos as well, but we're going to dive a little bit deeper on the idea in reference to the deep neural network. And how do we fine tune our model and deploy on our own, and advantages and limitations of deep neural network? All right, let's dive right in. Here's a very basic example of deep neural network: input neurons and output neuron. All these circles represent the neuron. These shaded orange bars represent the hidden layers. They are making the whole neural network deep, simply deep. Layers stacked after each other, making the whole idea deep. Just to reiterate from previous video, we randomly initialize these neurons based on standardization of weights and biases. Then we keep going further, get an output, compare the output with the real output. For example, the output here is 1, but the output that's supposed to be here is 2. Then we go back using the backpropagation algorithm, fix these weights and biases based on the gradient descent idea, and then come and repredict the output and see if there's still a lot of error left out. Then the loss algorithm, along with the backpropagation, we go back, fix the weights and biases, and now keep fine-tuning the model as there would be a need. But this is just a generic idea, but we want to learn how to really do it. To be able to really do it, one of the most popular libraries, or a very high-level library, is Keras. Keras is a high-level API for building and training these models. You could use PyTorch. Uh, it's a little bit more detailed compared to Keras, but we are going to use Keras for the most part in reference to this video. Keras is TensorFlow is embedded in Keras. So what I mean by that, Keras runs on top of the TensorFlow. So here is Keras, here is TensorFlow. So Keras is utilizing TensorFlow to make all the funky math computations that goes for the neural network. Why do we need Keras? We could just live with TensorFlow. Absolutely. You are more than welcome to use TensorFlow by itself, but you would need to do more low-level programming, define more details. Keras made things simpler for you. It has a lot of default settings for a model to run, and it gives you some fine tunings. Then you can play with it. For your first objective in developing a model is the model should run. Once the model runs, you can play with it, different hyperparameters of the model, fine tune it, do some feature engineering. But first requirement is obviously our model should run. So that's what Keras allows you to do. And it's pretty quick, pretty high level, easy to understand. That's the advantage. Now, going to the next slide, TensorFlow is a library which is embedded in Keras, as I mentioned. It's open source, developed by Google, pretty powerful with computations. It can work on both CPU and GPU. And uh, you need to install GPU drivers for GPU processing. It's very similar to NumPy. It's nothing too fancy. You're playing with the TensorFlows. TensorFlows are like NumPy matrix, but with more flexibility. You can build your own neurons with TensorFlow. You can define the full-blown architecture. You want the layers to be stacked. You want the layers to be separate. You want some layers to go deep, some layers to just not go as deep. And you can play with the whole model, break, cut, loop, whatever you want to do. Now you can train your loops, etc., using this TensorFlow. These are different packages that comes with TensorFlow. Uh, Keras, as we talked about, we got estimator, loss functions, metrics, test, train, and we could do a lot of feature engineering. We got a package called TensorFlow Audio. I'm not going to go too deep with this, but this is the high level overview of TensorFlow. All right. So TensorFlow provides you, biggest thing is n-dimensional array. Just like NumPy array, you can slice the NumPy array. Here in TensorFlow, you can even have a zero-dimensional scalar. You can have one-dimensional scalar, two-dimensional scalar, or you could have three or more dimensional scalar. So whatever you want your metrics to look like, you could use TensorFlow for that. Example, one-dimensional metrics. You just put a single constant in the matrix. You could have that's a zero-dimensional array. Here we got a 1D array. Here we got like a 2D array. You got x and y axis here. Now you got 3D array. You have more. You are going deeper within the array. So just to visualize it, you think that you're splitting a cell in Microsoft Excel. So you're putting more data in Microsoft Excel. All right. So here we have many different data types that could be handled by the TensorFlow. You have TensorFlow tensor, it's an immutable variable. TensorFlow variable, it's a mutable variable. Sparse tensor, etc. Then there are many type of operations. You could do square, add, exponential, etc. on those matrices. All right. So we will not focus on low-level TensorFlow. We're going to play with the high level, the Keras stuff on that works on top of the TensorFlow, so that we really are able to do the deep learning that we are really interested in, not the deep embedded math. We are not developing TensorFlow at this point. We are trying to use it and develop our understanding how deep neural network works. All right, let's start with an example. It's Airbnb data. We have looked at it a few times. It got 66 columns, and we are not doing feature engineering at this point. We are simply interested in predicting some of the outputs. So this is my target variable, price. It's a regression task. You see all these numbers. The price is a number, and it cannot be put, or it can be put right now. It's not a classification task. We have not put any classifications or categories. It's a simple regression task, each by itself. What I mean by that is rooms, price, we have different columns based, and they're indicating price of that room based on several different features or columns, right? So we got 66 columns. This is the first. How do we define the model? We say Keras.models are sequential. Sequential represents like these layers are sequential, one after another. We are making them deep. So it's just one after another. So we define the model using the Keras library and save it in the variable called model. And then we use the function add. Add means add layers. We say Keras.layers. That's what we are adding. How many? We are going to add those layers. This is my first input layer. And we got 66 columns in the input layer. So that's why I got 66 in the output layer. That's my output layer. I got one column or one output or one node in the output layer, and I've not used any activation function, right? So these two are my hidden layers. I'm using the activation function ReLU here, and I'm going to speak about what's ReLU, and we already discussed a little bit about ReLU in the previous neural network video. So this 50 and 50 is the number of neurons, how wide or how many neurons you want in the hidden layer. That's the question we are answering with this 50 here. These two are my hidden layers. It's simple. Model.add makes a layer add, or that's a hidden layer now. And we're using the Keras that works using TensorFlows, and it's making the whole thing dense. Dense indicates that we are doing a hidden layer. Input indicates that we are doing an input layer. And dense 1 indicates that we are doing output. This is my output, and we define the activation function here, typically. Right now, I didn't define any. All right, why I didn't define any activation function, we're going to learn in future slides in a couple of minutes. Right. So that's my model, and this comes with some default settings in the background. Even if you do not explicitly define those, what are those default settings? Kernel initializer is Glorot uniform. What's Glorot uniform? We're going to learn in a couple of slides from here. So we are now talking about initializer. We're going to talk what's Glorot initializer. Why do we need an initializer? Why cannot we just initialize our neurons randomly, just like we did in neural networks or in the previous video? The problem is vanishing and exploding gradients. What happens during the backpropagation, we are trying to change the values of weights and biases based on gradient descent algorithm. Gradient descent algorithm works on the loss function. Loss function is predicted value versus the actual value. So we're not working on the test. We are just working on the known data to learn. Now, compared to the output that's known, we are comparing the output of from the from the uh, from the dense layers or from the neural network. We compare the output, we see, and we know the actual output. We compare both of them and realize that they're not matching. Now I keep going back, keep fixing the weights and biases based on the gradient descent, based on the loss function, and come back again to predict the output layer or output neuron. So what's vanishing gradient is both of these lead to a solution not converging. So vanishing means obviously vanishing. There is no gradient at all at that point. It gets so low, it's such a small number now at this point that it's not able to change the weight or weights uh, when it propagates through the different hidden layers through different neurons. So we want to make sure that when we are randomly initializing the neurons, uh, we do not have a problem of vanishing and exploding gradients. Here, the value of gradient is too small. Here, the value of gradient is too high. That leads to very large weights, or this leads to very small weights. Lower layer weights remains unchanged. So you're not even able to change the weights. So you're not fixing the error. So you're not learning enough. That's the problem of vanishing and exploding gradient. That was a problem for a very long time. How do we fix it? Using Xavier-Glorot initialization. What it does, it keeps your mean 0 and variance that's based on this formula. So formula is f fan in plus fan out over 2. In means how many neurons you got in the input layer and how many neurons you're going to go to the output layer. So you do this math, take the average and you divide that by 2. So that's going to be your 1 over variance. So that's going to be your 1 over fan average. So that will give you your variance. So keeping this formula intact, we make sure that the variables are uh, that the initialization of weights is done using a formula rather than randomly. So this led to huge success in the field of deep learning. Do we just have Glorot? No, we got a few more. We got Glorot initializer, we got He initializer, we got Leaky initializer. They all work nicely with different kind of activation functions. Sigmoid goes pretty nicely with Glorot. He goes pretty nicely with ReLU, Leaky ReLU, ELU, GELU, Swish, Mish. We got all these kind of activation functions and different uh, different variants here are defined. 1 over fan average, 2 over fan input, 1 over fan input. So these are math that researchers came up with, and it works pretty good. and improves the accuracy. All right. So let's learn a little bit about this activation function that I just spoke about. So our model, we looked at ReLU as our activation function. What is this activation? What are we activating? We talked about this in our previous video, where we have an activation function that kind of turns on and off based on uh, the x-axis information. What is the x-axis information? It's the sum of weight, biases, and the value at the neuron. And if it's in this range, it turns it into y values, and y value only ranges from 0 to +1 for sigmoid. So this is just sigmoid. And we just talk about to fix that for problem of exploding and vanishing gradients with sigmoid, we want to use uh, the glow rod initializer, and that's the default setting in Keras. But you could change these activation functions based on different activation functions. So if you're not using sigmoid, if you're using ReLU as your activation function, then you can go to he as your initializer. All right. So this is the ReLU chart. There is no value on the y-axis. If you're however negative you go in the x-axis, there is practically zero value on the y-axis for all of that. So that leads to a problem called dying neurons. A lot of times you got hidden layers, so many neurons, a lot of these neurons would just simply die and kill themselves because there's no value output. And these neurons are at this point not transferring or transmitting any more information. That leads to dying neurons. So what do we have a fix? We have this fix called leaky ReLU. It allows a little bit of value transfer, some information transfer, and it works pretty well for the most part. So it produces a value that's close to 0, but eventually it could wake up in further iterations. So we still keep that value of we still keep that neuron from not dying, so that in future it could still be used during backpropagation or future iterations of the neuron. So how do we define that? We define leaky ReLU this way. We add a layer, add layer. We talked about that. Add tf.keras.layer.leaky ReLU, and alpha is the learning rate, and that's how we define the leaky ReLU as my activation function. Alpha is the measure of how much the function actually leaks. I'm sorry, it's not learning rate. It's the measure of how much the function leaks. So you need how much leak you need, you can define that using this value of alpha. All right, we got another activation function which is very similar to ReLU or leaky ReLU, I would say. We got, instead of a straight line, instead of linear, we got like a parabola here. So slope is 1 in the positive side, and this speeds up the gradient descent. But the drawback is that it's slower than ReLU because it's a little bit longer formula. Or it's a second degree polynomial at least. Advantage is it converges faster. So for the most part, leaky ReLU or LU would work for the most cases. All right, activation function, different kind of activation we have is our ReLU, CELU, GELU, swish, mish, and these are different activation functions plotted here. Implementation is pretty simple. You just change the value here with all these guys, and that's how you implement these LU, CELU, mish, swish, then hyperbola. We can use ReLU for the most cases. As I just mentioned, I would say I would use leaky ReLU because it prevents the problem of dying neurons. Here are the basic rules, very strict rules that we want to abide by. For a regression task, we want to always say activation is none in the output layer. So this is my output layer. We want to say output activation is none, and the final output would be just one neuron or just one value for the regression task. For that row, for each row, we got only one output or one neuron output. That's how this works. In regression, if you mess this up, you're going to struggle making a model to run. So last layer must have only one neuron. Last layer should not have activation function. So you should always say none here for regression task only. All right. For binary task, you have sigmoid as your activation function, and still you have output neuron only one. For a given row of inputs, you have only one output possible. If you mess this up, model is not going to run. It's just very basic rule. What if we have a multi-class classification? We use an activation function called softmax. For a given row, it produces 4 outputs. Where is this 4 coming from? It's the number of class. So if you divide that data set into 4 categories, greater than 226 price, smaller than 75, between 75 and 150, and one more. Uh, so 4 tasks for 4 classifications will lead to 4 outputs. So you have defined softmax as your activation function. What it does is it produces 4 outputs. What are we going to do with 4 outputs? We are going to see the probability. This output A, the chance of being greater than 226, for example, is 70%. B output is just 0.1% or 10%. The other one is 20%. And this D output is 0%. So it gives you the probabilities of the final categories. And we talked about softmax in previous video, how softmax works. It always produces output in the form of probabilities, which we could use to define or understand which out of 4 categories or 3 categories or whatever number of categories you got, uh, we have the probability for them. Here's pretty important technique to reduce uh, overfitting. It's called batch normalization. It reduces overfitting, and it also works very nicely with vanishing and exploding gradient. So what it does, you add these two in Python, this 2 line of code. Pretty simple, right? Add batch normalization, model.add batch normalization, open close parentheses. Now you're calling this batch normalization package or function. What it does is it standardizes the input of that layer. It normalizes the input, and it makes sure that there is no chance of exploding and vanishing gradient. It's like giving every neuron a fresh and clean input. Batch normalization improves the stability and speeds up training, and even acts as a form of regularization. All right. So let's learn about batch normalization a little bit more. It's great for processing the images. It's mostly used with the large language models because you run into this vanishing and exploding gradient problem even more. So it even works like a regularizer. And if you apply this before the first input layer here, you don't even need to standardize your input or activate input for the activation for the neurons input layer. We talked about what is standardization in previous video and so many previous videos. So you don't need to standardize that data if you use batch normalization before this input layer. You can send unstandardized data. For example, you can send the text as is to the batch normalizer, which converts it or which regularizes it on the input layer. The disadvantage is it slows down the overall process because it's acting on that layer, doing some more math on it. So batch normalizer reduces your vanishing and exploding gradient problem because it's giving a fresh start, normalized values or clean values that are not too small, not too large during the process of learning or fixing the weights and biases. After defining the model, we need to compile it. How do we compile? We are interested in mean square error. You know, mean square error is the loss function that goes only with regression task. What do we do when it's a classification task? If it's a classification task, we use the loss function of sparse categorical cross entropy. If it's a binary task, we use binary cross entropy. These are the formulae for binary cross entropy. It's a loss function. Again, I repeat, loss function is simply calculating the losses that happen during the prediction process. So it's simply using gradient descent to compare the actual value with the predicted values. So why do we not use the binary For binary, why do we not use the mean square error as my loss function? I don't use that because it produces this kind of output, 0.04. For example, actual is 1, predicted is 0.8. The loss is supposed to be close to 0.2, which is the output from binary cross entropy. But if I use MSE, I have an output of 0.04, which does not make any intuitive sense to me because I got a better idea using cross entropy. What's optimizer now? Optimizers, um, once the model is defined, we compile it. And we're trying to specify the optimizer, how the weights update. In deep learning, optimizers are algorithms used to adjust the weights and biases of neural network to minimize the loss function. So backpropagation algorithm computes the gradients, works with gradient descent as the base algorithm. And what optimizer does, the optimizer algorithm, it updates the weights using those gradients that are computed with the gradient descents. So it works hand in hand with the backpropagation algorithm. And we are using ADAM or ADA-M as my optimizer. ADA-M represents adaptive momentum. Do we have more optimizers? Yes, we got ADA-MW, ADA factor, adaptive factor, Lion, SGD, which is like the legacy optimizer in TensorFlow. So what does this optimizer ADA-M or adaptive modeling really do? What it does is it's again based on stochastic gradient descent. So how it's different from stochastic gradient descent? Stochastic gradient descent takes bigger steps in the beginning and takes smaller steps uh, as it walks further. When you talk about steps, I really mean the tangent. So imagine there's a steel bowl with a steel ball and it's walking down. So it initially takes like larger steps, stochastic gradient descent. And as it goes down, its step size or tangent size keeps going smaller. This is the optimal solution for the stochastic gradient descent. But when we talk about the adaptive momentum, it does the absolute opposite of stochastic gradient descent. It starts slowly, but reaches the terminal velocity at the bottom. Starts slowly, but reaches the terminal velocity at the bottom. It can escape plateaus and some local minima, but it still is based on stochastic gradient descent idea. The advantage is it has some level of learning from the previous tangent. Momentum represents some level of memory, and adaptive is it's using that memory to adapt and kind of size its jumps. So it's kind of an improvisation of the stochastic gradient descent, but it's using SGD or uh, gradient descent idea as its baseline algorithm. We got few more ideas for optimizers. These are pretty new ones. They were not there before. I would say 10 years back. Adaptive W, Lion, ADA factor. ADA always represents adaptive. All these are improvisation over the gradient descent. Here, um, in the adaptive W, it's still based on the stochastic gradient descent. In Lion, it's based on stochastic gradient descent, but it also tracks the momentum, and it's more memory efficient than ADA-M. What ADA factor does, it takes less memory and can be used for natural language processing. We're going to use optimizers in the example that we are going to do, and we have realized that it makes a substantial difference in the accuracy. How do we define the optimizers? Just when compiling the model, you can say optimizer equals to ADA-M. And similarly, if you want to do like a full line, you want to define more parameters pertaining to the optimizer, you could do it this way. Optimizer equals to tf.keras.optimizer.ada-m or some other optimizer if you want to use that, and you can define the learning rate. Now, what's learning rate? Learning rate is basically, if you have the high learning rate, it can diverge from the solution. If you have the low learning rate, your solution can take longer time to converge. How do we go about this situation? So we start high, so we work faster, and then we reduce the learning rate gradually, so we learn and improve our accuracy. Different kinds of learning rate algorithms are available. One is exponential decay, piecewise constant decay, polynomial decay. So these are all decay functions, cosine decay restarts, and we can define their decay rate. Uh, all these are different ways to schedule the decay or different ways to schedule the learning. Another interesting way to schedule the learning rate is through LR schedule. That's another algorithm to work with the learning rate. So um, we are going to use the learning rate to train our deep neural networks, but it's not necessary that we have to define it because our default learning rate is already defining Keras. Now, DNNs are susceptible to overfitting. We already talked about overfitting. That's the idea when train accuracy is higher than the test accuracy. So when we're doing the real world example on test data, the test data is not performing, the accuracy is lower when compared to train accuracy. That's called overfitting. And how do we fix the overfitting problem? We fix it by dropout, early stopping, and L1, L2 regularization. That mostly pertains to regression task and early stopping. Let's look at what early stopping is, but let's look at what's dropout. Dropout is essentially dropping out the neuron in the layer. Which neuron to drop? Just randomly any. Now, why do we want to drop out the neuron? We want to reduce the learning in the in the train data set. So the test and train accuracy come out to be closer. So we reduce the learning a little bit by randomly dropping out the neurons. We only do this dropout method when we have this overfitting problem. When you don't have this overfitting problem, you can simply not use the dropout method. How do we define dropout? Just when adding the layer, you can say dropout is 2%, just drop out the 2% neurons, like layers.dropout, and it will do the needful. Now, when do we early stop? When the test and train accuracy start diverging from the solution, we use another parameter called patience. We'll keep some level of patience, and we'll observe for 5, 6 iterations if test and train accuracy are diverging or increasing. So here is fairly close, but after this point onward, the accuracy of test and train are diverging. So for example, here we define this early stopping here, we define this patience here, and we are using monitor the loss function. And we could do this whole thing in batches of size 100. Smaller the batches, more stable the model will be. Larger batches, model tends to crash more. And sometimes it underfits too if you have like larger batches. All right. So this technique of L1 and L2 regularization, we want to talk about this. This is the exact same deal that we talked about in our previous videos. We could use L1 and L2. These are like the brakes in your car, kind of reduce the learning accuracy in the train data set, and that applies to test. So kind of test and train come closer, and that's how we reduce the overfitting problem. Now, what's transfer learning? Transfer learning is transferring the learning from previously learned model. For example, OpenAI model, if you somehow get access to that OpenAI model, uh, you could, if they allow. I don't think they allow you to do this full thing in this conventional fashion, but I know that Llama does, and there are a few other open source model like Hugging Face, etc. So they'll freeze these layers, but they will give you access to some of the hidden layers and the input layer, or not even sometimes the input layer. They'll just give you access to the hidden layers so that the learning is transferred, and you can put your own. You can train your own. You can add your own layers on top of previously learned layers. So you have like a big base, big strong base, and on top of that, you build more stories to it and optimize it to your own data set. That's how transfer learning works. All right, we are right at the summary and recommendations. You could use TensorFlow or PyTorch to achieve same or similar output. PyTorch has become more recently accepted because of its ability to work on distributed systems. And TensorFlow, as part of Keras, is another interesting library that Google has actually developed. And we are sticking to this for our example purposes. Just to reiterate, in our previous videos, we talked about how do we handle regression. We use mean square error as my loss function. We will always define none as the activation function in the last layer, and we will always have the last neuron as 1. Same deal, last neuron must be only 1 for binary, and we use binary cross entropy for binary classification, and we use sigmoid as the activation function for the most part in binary classification. And if it's multi-class, we need to match the number of neurons to the number of classes, and we use softmax to get the probability of those classes, and we use sparse categorical cross entropy. Right? In rare cases, we could use the one-hot encoder to convert the categorical into numerical target variable. So if it's still categorical, we would be using a categorical cross entropy with softmax as my activation function. You know what softmax does? It converts the output into probabilities. So if you got 3 categories, A, B, C, and we converted them using one hot encoder, oops, one hot encoder to 1, 2, and 3, we would still get the probabilities as output
For example, zero point 0.5 for this one, zero point 0.3 for that one, zero point 0.2 for that one. So we are going to use this as my highest probability outcome. Just note that we would still need to have the same number of neurons in the output layer as the number of categories that we have in the target variable. Here's the interesting part. In scikit-learn, you cannot do this deep and shallow network together. Here you can slice the network. For example, few of the inputs from the input layer can really go directly to the output layer, and some of the inputs at the same time can go through multiple hidden layers. So you have the ability to slice the input layer in Keras packages. All right. The steps to build a deep neural network: create your model definition, decide on the following parameters, including the number of neurons, number of layers you want to add, activation function, optimizer, learning rate, initialization, and so on and so forth. We also got the Keras tuner to do the grid search. We did grid search in the previous videos that runs through a range of parameters and finds the most optimum parameters. Similarly, in Keras, we got Keras tuner to run through the bunch of different parameter ranges. Let's say try 3 different kind of optimizers and see which one performs or has the highest accuracy. So you got a bunch of decisions to make before you run like a deep neural network with Keras. Here's my recommendations. Start with a single hidden layer. Most of the cases, a single hidden layer is just good enough, unless you're trying to work with some image processing. All right, add layers until there is overfitting. If you realize that your train accuracy has reduced from the test accuracy significantly, then you call it overfitting. And then you want to reduce your overfitting, you could reduce your hidden layers as one of the starting steps. Complex relationships typically require deep neural networks. So just understand what kind of data you are dealing with. Are you dealing with way too many columns to learn from? And they don't seem to have any patterns initial to start with. Number of neurons per hidden layer should be the input and output layer needs to be predetermined before you start running the model. Most common approach is the funnel shape. So when I say the funnel shape, we mostly looked at the rectangular shape. So same number of neurons in all the layers. So if you got 4 in the initial layer and you're defining 4 in the hidden layers, 4 in the other hidden layer, and as you keep going, finally the output layer may have 1 or 2 or 3 based on whether you're dealing with categorical binary or uh, regression task. So that's my output layer, but this is not funnel shape. So when we talk about funnel shape, it's like initially starting with large number of neurons and then keep reducing them gradually. So that's my funnel shape. How do we define funnel shape? It's pretty easy with Keras. You just say to Keras that my neurons are going to be in the funnel shape, and it takes care of how many neurons it's going to put in to make that shape happen. There are a few other approaches. Pipe shape, inverse funnel shape, use early stopping and regularization to prevent overfitting with this one. So if you do like an inverse funnel shape like that, you need to use regularization and early stopping because you're learning way too much as you get further away from the initial nodes. Some of the open source models that you could really learn, you really run on your personal computers, you can download Llama. It fairly has good performance. If you got NVIDIA RTX 4060 or better graphic card, we got GPT-2, BERT, Whisper Speech, Stable Diffusion. All right. You could download these free models, generative AI models, and run on a personal computer. It may not be able to handle all the greatest tasks, but it will serve some of the purpose on your local PC. And these are freely available to download. All right. Some of the recommendations further include learning rates start with small values like 0.01 and increase as needed. Use learning rate scheduling when necessary. And this is my favorite optimizer, ADA-M or ADA Adaptive Momentum Optimizer. Activation function, my most popular activation function is ReLU. I sometimes use Leaky ReLU as well. The Leaky ReLU, which has a little bit of leak over the ReLU function. Number of iterations, we call them epoch in machine learning. So higher the number of iterations, better the learning, but use it with early stopping so that it does not do overfitting. That brings me to the end of my presentation. I hope we covered all the topics we promised. We are going to dive right into Python code in the next video.